Computing area is really hard. Outside of a few simple shapes, like rectangles, triangles, or circles, you're probably not certain what you would do. For example, let's say that I asked you to compute the area under the graph of f of x equals x squared on the interval 0, 1. What would you do? Let me graph this for you so you can visualize the problem. Now, this isn't something that we know how to attack. It's not a usual shape. Nonetheless, a lot of real-life application depends on our ability to find these areas. Our goal will be to develop a procedure which will allow us to easily compute such areas. So with that in mind, we'll define something called the definite integral. Suppose that f is a function defined on an interval ab. The definite integral of f on ab, which we'll denote with this weird stretched s thing, is defined to be the signed area between the x-axis and the graph of f. There's a few points to make here. First, let's talk about notation. The a at the bottom of the s here is called the lower bound of integration. It tells us where our integral begins. In the same vein, the b is the upper bound of integration and is where the integral ends. And this dx term, it's a bit complicated to explain. For now, you should pretend that it's telling you what variable you're integrating. And one last thing before we start doing examples is what I mean by signed area. This means that area beneath the x-axis will be considered negative area, while anything above the x-axis will be positive area. If I draw a generic function, I'll highlight negative areas in red and positive areas in green, like so. Okay, let's start doing some examples. I do want to say though, before we start, that the examples that we're about to do are not representative of how we actually compute these things. Rather, my goal is to familiarize you with the notation and intuition of integrals before we start the real work. With that being said, let's find the integral of the function 2x on the interval -1, 3. Our argument will be geometric, so let's draw a picture to help us visualize the problem. The area beneath the x-axis will be negative, and the area above will be positive. We'll compute the areas of each region separately, so let me label these regions so we can refer to them later. Starting with the dagger area, which is the function on the interval -1, 0, this is a triangle with height 2 and width 1. Our area is thus 1/2 width times height, but negative because it's beneath the x-axis, giving us an area of -1. For double dagger, on the interval 0, 3, we again have a triangle, but this time with width 3 and height 6. This gives us a positive area of 9. Thus, the definite integral is the total signed area, which in this case is 9 minus 1, or 8. Next up, let's do a slightly different kind of example. Let's find the integral of root 9 minus x squared on the interval 0, 3. The trick here is going to be figuring out what familiar shape is given by the integrand, root 9 minus x squared. If we set y to be the square root of 9 minus x squared and do some manipulation, we get this. So this tells us that the graph of our function is the top half of the circle centered at the origin of radius 3. Now the integrand just asks us for the interval 0, 3, which I'll shade in here. And this area is 1/4 of the area of the total circle. So the definite integral is 1/4 times pi times the radius squared, or 9 pi over 4. So right now, the definite integral is just notation. We'll see later some more interesting techniques for computing integrals.